question 6. In an Argand diagram, the points A and B represent the complex numbers 5 plus 4i and 1 plus 2i. So A is the point 5 plus 4i, and B is the point 1 plus 2i. Or they represent those complex numbers. Given that A and B are the ends of a diameter of a circle, find the equation of the circle in complex number form. Right. Okay, well, I mean, this is all right. In core 1, we can be given 2 points in space, and we can be asked to find the equation of the circle. We've just got to kind of reframe that in terms of this. So, I don't know, maybe it's helpful for us to think in core 1 terms. A is the point 5, 4, and B is the point 1, 2. Okay, that's a useful thing to think of, isn't it? They would be the coordinates. So if we were finding the centre and radius of the circle, we'd need to find the length of AB. This is just core 1 stuff. The length of AB is, remember, it's the square root of y2 minus y1, or x2 minus x1 squared plus y2 minus y1 squared. It's that. So this gives us the square root of 4 squared plus 2 squared. That's, what's that, 20, isn't it? That's root 20. And root 20 is 2 root 5. So we've got a diameter of 2 root 5, which gives us a radius of root 5. That was a good thing to establish to start with. Yeah, that seemed like a reasonable way to do it. The centre of the circle is the midpoint of those two. Again, this is just core 1 stuff. The midpoint, we do 5 plus 1 over 2, and we do 4 plus 2 over 2. So the midpoint has coordinates 3, 3. There's the midpoint of our circle. Now, we're in complex number terms, so that is the point that represents the complex number 3 plus 3i. Now, the question did say, give your equation of your circle in complex number form. So although in core 1 at this point we'd now write brackets x minus 3 all squared plus brackets y minus 3 all squared equals 20, in terms of this we don't do that. In terms of this we need to put it into complex number form, which is the modulus of z minus our centre of the circle is equal to the radius of the circle. That's the equation in complex number form. And I think that's acceptable. Maybe we could have written it like that, because that's the way that we normally get these presented. But that was fine. You get your mark for the first time you do that. You alright, Alfred?
I only got 3.
Did you get that completely right?
Yeah.
Oh, well.
I
There you
didn't
go.
do the very last explanation.
You only got 3 for it.
Yeah.
Maybe there is your well, we'll look at that in a moment. Okay, then it says the perpendicular bisector of AB is denoted by L. Alright, well hang on, let's think this through. AB is the diameter of a circle. So the perpendicular bisector of a diameter. Perpendicular bisector of that would also be a diameter of a circle, wouldn't it? So we're looking for a circle with another line drawn through the centre. Sketch C and L on a single Argand diagram. You know what they do when they get you to do circles and Argand diagrams. Very commonly, there's some little trick going on where it touches one of the axes or it goes through the centre. So let's just mentally think through that, or it goes through the origin, rather. Does this? Well, it doesn't, does it? Because that's not the modulus of that number is not the same as the radius, so it doesn't go through the origin. Root 5. Well, what is root 5 as a number? It's smaller than 3. It must be smaller than 3, mustn't it? It's a little bit more than 2. So the radius of that's the point 3, 3, that it's not going to touch either axis either. So as we come to draw this, actually what we're looking for this time is a point there and a circle that is just there, hopefully with the centre looking almost like it's in the centre. It's not touching either axis, it's not going through the origin. That's the point 3 plus 3i, that's what that number is represented by. Let's think through some of the other things that we've got here. A was the point 5 plus 4i, was it? So A is, what's that? That's over there somewhere, isn't it? We weren't asked to mark A, I don't think. And B is the other end of the diameter, so that's 1 plus 2i, so D, that looks about right, there, on the circle. And we are looking for our line as perpendicular bisector of the line AB. So the line L must be a line that goes to like that. Okay, perpendicular bisector. There it is. So that's my diagram for however many marks that was. 2 marks. And then the question said, now this looked at first glance like it was going to be difficult, but find the complex numbers represented by the points of intersection of C and L. There's a number of ways we can do this. We can start thinking, we could do it completely algebraically if we really feel inclined. We could go back to core 1 style. We could do the core 1 equation of that circle. We can find the equation of that line, because we could find that gradient, it's perpendicular to it, we know what point it goes through. So we could do it completely algebraically. Or we can think a little bit about, well, the method that I thought about was similar triangles on this. I very, very lightly drew one here. You see that triangle there, you see that little right angled triangle? That triangle is one that goes across 2 units and up 1 unit. Now by similar triangle stuff, there must be a triangle there that goes up 2 units and back 1. Does that make sense? And that triangle takes us to the point at the top. So, that is going to be, I'll write it on here I think, from point C to A, we go across 2 and up 1. So from C to that point, we're going to go 3 plus 3i, we're going to go back 1 and plus 2i. So that point at the top is 2 plus 5i. Does that make sense? And that's one of our numbers, that's the point at there. And this point down here, to get to this point we must go across plus 1 and down 2. So that point is 4 plus i. And that was how I approached that, completely geometrically. Just think about the similar triangles and the ratios that were involved and all of that. As I say, if you were really inclined, you could turn it into algebra and do it as intersection of a line and a circle. But probably cool, really, isn't it? There we are. It looks easy like that, doesn't it? That's maths.